Okay, so now we're going to be working on proving some of the properties about quadrilaterals. We are going to prove that opposite sides of a parallelogram are congruent. We're given parallelogram ABCD, and we want to prove that either AB is congruent to CD or AD is congruent to CB. I'm going to show you how to prove the first one, that AB and CD are congruent. So, step 1 you're given always. We have parallelogram ABCD. Now what we're going to want to do is we're going to want to draw in an auxiliary line here. It's the diagonal BD of this parallelogram. We need to state that in our proof. BD is a diagonal. That's our auxiliary line. Now, we know that in a parallelogram, opposite sides are parallel. That's the definition of a parallelogram. So I can say that AB is parallel to CD. I can say that BC is parallel to AD. And from here, there's many different ways that we can go. Looking at BD as our transversal, I can say that ABD, angle ABD, and angle CDB are congruent because those are alternate interior angles. I can also say that angle ADB and angle CBD are congruent because those are alternate interior angles. So that's the alternate interior angles theorem. Then, by the reflexive property, BD is congruent to itself. And so if I look at these two triangles here, those two triangles are congruent by angle, side, angle. And so if those two triangles are congruent, then we know that parts of the triangles are congruent. So I can say that AB is congruent to CD by CPCTC. All right, so we proved that a pair of opposite sides are congruent. You can also prove right away that AD and BC are congruent because the triangles are congruent. So we could actually prove both of these within that last step. All right, moving on to the next proof. So we are going to now prove that the opposite angles of a parallelogram are congruent. You can use this same exact proof and then just at the very end say angle A is congruent to angle C by CPCTC, but I'm going to show you a different way to prove that the opposite angles are congruent. There is also, we're going to prove it using congruent triangles, but there is a way to prove it without using congruent triangles, and I'm going to challenge you guys to do that for your worksheet. So we are given parallelogram ABCD, and we want to prove that either angle A and C are congruent or angle B and D are congruent. I'm going to prove angle A and C are congruent. So I start off, and I'm going to prove it using congruent triangles. So I'm going to start off by using my auxiliary line BD. And then I know that since this is a parallelogram, that opposite sides are congruent. So I can say AB and CD are congruent. I can say BC and AD are congruent because a parallelogram, we have two pairs of opposite sides congruent. And then lastly, I'm going to say that BD is congruent to itself by the reflexive property. So these two triangles here then are congruent by SSS. And so therefore, I can say that angle A and angle C are congruent by CPCTC. Again, you could have done this same exact proof, and then your last step would be angle A and angle C congruent by CPCTC, but I showed you a different way. All right, moving on to the next page. We are now going to prove that the adjacent angles of a parallelogram are supplementary. This is a pretty simple proof, especially since we know that we have parallelogram ABCD. If you have parallelogram ABCD, you know that opposite sides are parallel by the definition of a parallelogram. So I can say AB and CD are congruent. Parallel. I can say BC and AD are parallel. And that's just the definition of a parallelogram. Well, if we look at this transversal, then I would know these two are supplementary by the same side interior angles theorem. Or if I used this transversal, I could say these two angles are supplementary by the same side interior angles theorem. Or if I used the two side parallel lines with this transversal, I can say these two are supplementary. Or if I use this transversal, I can say these two are supplementary by the same side interior angles theorem. So basically the third step, you just pick one of these two angles here. I chose this one here, and they are supplementary by the same side interior angles theorem. That's it, a 3-step proof. All right, and moving on to our last proof of the video, we're going to prove that the diagonals of a parallelogram bisect each other. Now this is probably the most challenging one. I'm going to show you how to do DE congruent to BE. And so we're given parallelogram ABCD. The reason why this one's more challenging is because instead of us focusing on these large triangles here, we are only going to focus on these two triangles here. Because BE is involved in that triangle I outlined in green, and DE is involved in that triangle that I outlined in pink. All right, so focusing on those two green triangles, we're going to get started. So a parallelogram has opposite sides congruent. So I can right away say that AB and CD are congruent because we know that we are given a parallelogram and opposite sides are congruent in a parallelogram. It would not be beneficial for us to say BC and DA congruent because those are not involved in that green or pink triangle. Now I can also say that AB and CD are parallel because that's the definition of a parallelogram. And so if I have those parallel lines cut by this transversal here, I can say that angle ABE is congruent to angle CDE by the alternate interior angles theorem. You can also use these two parallel lines in this transversal to say angle BAE and angle DCE are congruent by the alternate interior angles theorem. I did not do it that way. I instead used that angle BEA and angle DEC are congruent by the vertical angles theorem. So thus I proved these two triangles congruent by angle side. Now if you used both pairs of alternate interior angles, then you would be proving these two triangles congruent by angle side angle. So just making you aware of that. So since I have these two triangles congruent, now I can say that the parts are congruent. So I can say DE is congruent to BE by CPCTC. All right, that brings us to the end of this lesson. More proofs in the next video.